Hey, welcome back. And today we're going to start talking about the ratio test. And so before I get into the theorem and go over the theorem really quickly, the ratio test is really nice because you don't need to, well, including the root test too. The ratio and root tests are nice because you don't have to find a comparison series to compare it to. So with the ratio test, we take series and we compare it with the next term. So we take the ratio of the terms. And why is this important? Because we can use this to test things like, for example, when we look at the harmonic series 1 over n, and we compare that to the series 1 over n squared, the issue wasn't that it doesn't go to 0, because remember, the nth term going to 0 was not a sufficient condition for the series to be convergent. Remember that? And so in that case, we couldn't use the fact that it was just going to 0 because 1 over n and 1 over n squared both go to 0. It was the fact that 1 over n, the harmonic series, doesn't go to 0 fast enough. And so the ratio test is a way we can find out whether it does go to 0 fast enough, and then we can determine whether the series converges or diverges based on that. And so that's where we stop. Okay, and so with that being said, let's go over the ratio test. So the ratio test says that if we let this be a series with non-zero terms, and then we let the rho equal the limit as n approaches infinity of the ratio of the n plus 1 term divided by the nth term, if that ratio, that rho, if the limit of that rho, if rho is between 1 and 0 inclusive, so if it includes 0 but less than 1, then the series converges absolutely. If rho is greater than 1 or is equal to infinity, then the series diverges. And if rho is equal to 1, then the test is inconclusive. Okay. So in the next video, I'm going to do a proof of this. So we'll go through the proof in the next video, and then we'll do some examples. Okay, see you then.